So reactions involving gases. We've talked about some reactions that produce gases, but there are also reactions that can occur between gases. And we haven't learned how to predict products of those, but we can still do calculations about such reactions. So when we have gases that are, when we have reactants or products that are gases, we tend not to identify their quantities by mass, because gases are hard to weigh. It can be done, but it's not easy. So we tend to express their quantities as volumes at a given pressure and temperature. So if we have the pressure, the volume, and the temperature of a gas, we could calculate the number of moles, and moles is what we need to do stoichiometry calculations. If we have the number of moles, the temperature, and the pressure, we can calculate the volume. And so we're using the ideal gas law to find the moles of a gas, or from the moles to find the volume. If the reaction is at STP, then things become simpler because we can use the molar volume of a gas. So always look for at STP. That means the problem is going to be easier. You could see partial pressures in a reaction like this, so don't be surprised by that. Here's the general plan for stoichiometry: grams to moles to moles to grams. When we're dealing with gases, we're going to mix it up. So if you're starting with an amount of gas, you're going to have pressure, volume, temperature of a gas. You use the ideal gas law or molar volume to convert to moles of that gas. And then you use the stoichiometric ratio, the mole ratio, to get to moles of your other thing. And then depending on what they're asking you for, you may need to use the ideal gas law again. Any questions on the big idea? So let's do an example. In the following reaction, 4.58 liters of oxygen was formed at a pressure of 745 millimeters of mercury and a temperature of 308 Kelvin. How many grams of Ag2O decomposed? So here's our balanced chemical equation. You heat the silver oxide, and it decomposes into silver and oxygen. So we should identify this as a stoichiometry problem because we're given information about one substance and asked about a different substance. That means there's a chemical reaction occurring. It's not a dilution problem or just a changing pressure or volume of a gas. All of those things deal with just one substance. Here we've got two different substances. So we'll use this balanced chemical equation to organize the information. 4.58 liters of oxygen, pressure of the oxygen gas, and the temperature of the gas. And then the question has to do with the silver oxide, and they want to know how many grams. So our overall plan here, our path, is we've got pressure, volume, and temperature of oxygen. So we can go to moles of oxygen, and then to moles of the silver oxide, and then to grams of silver oxide. To go from pressure, volume, and temperature to moles, we have to use an equation here. It's not just a conversion factor. This is not occurring at STP. So we have to calculate that. So we take the ideal gas law, we rearrange it, we come up with N equals PV over RT, because we want to know the moles. So what's the pressure? We need to convert it, because the ideal gas constant tells us what units we need to use, and we need to use atmospheres. So it's 1 atmosphere over 760 millimeters of mercury. Calculators. Not here. Awesome, thank you. Actually, there is. You know what? That's right. Somebody left TI-36X Pro. How convenient. I left mine on my desk. 745 divided by 760. So 0.98026, that doesn't look like a 6, atmospheres. Okay, so I'll put that into the ideal gas equation here, 0.98026. And I'm just trying to demonstrate keeping track of sig figs as you do your problems. The volume, 4.58 liters. We don't need to convert that unit. And then we divide all of this by the ideal gas constant, 0.08206. The units on that are liter atmospheres per mole Kelvin. That's what tells us that we need to use atmospheres for the pressure. And temperature always has to be in Kelvin for gas problems, 308 Kelvin. So 0.98026 times 4.58 divided by 0.08206 divided by 308. So that gives me 1776, which makes me think of 76 trombones because my son was in The Music Man recently, and I'm afraid I'll be whistling later. Moles of oxygen. Did I do that right? Now we're going to use dimensional analysis. So I'm going to convert from moles of oxygen to moles of silver oxide, dividing by moles of oxygen so those units cancel out. And then I need another term here where I've got grams of silver oxide over moles, so I can get rid of moles of silver oxide. Mole ratios always come from the balanced chemical equation. 2 moles of silver oxide produce 1 mole of oxygen. Then I need the molar mass of silver oxide. It's 107.9. I've almost got that one memorized. 107.9, that's the mass of silver, plus 16 for the oxygen. $231.8. So 231.8 grams per mole. So I take my number of moles, I multiply by 2, and I multiply by 231.8. And I get a mass of 82.351 grams of silver oxide. And for sig figs, that's going to be 82.4 grams.
So on the sig figs, you're going to take the sig figs from the previous calculations?
Yeah, so on the sig figs, I have to consider the entire calculation, this whole big mess here. So when I calculated the number of moles, I paid attention. I converted my pressure here. This had 3 sig figs. This is exact. So this has 3 sig figs, but I'm carrying 2 extra digits to avoid rounding errors. The volume has 3 sig figs. This ideal gas constant has 4. The temperature has 3. So then this amount of moles had 3 sig figs. And this is exact. This had 4 sig figs, so my final answer has 3 sig figs. Ideally, all of you would be able to do that and would do that on every single problem. I recognize that that's not going to happen. Sometimes significant figures are more important than other times. You probably need to pay more attention to them in lab than you do when working homework problems. As a shortcut, if you just really, really hate sig figs, I don't know if you've noticed, but most of the problems that we do end up with 3 sig figs. So if you're just not really good at sig figs, guessing at 3 or 4 is probably going to be safe most of the time. Any other questions?
So what about, like, I've also noticed that a good chunk of the time your sig figs are the same number of sig figs as the information that you're given in.
Yes. Many times the number of sig figs in your final answer is the same as the number of sig figs in the data that you're provided. Because usually that's what's going to limit your precision, the number of sig figs. We would not want to have this rounded version of the ideal gas constant limit our significant figures. We don't want to have our molar masses limit our number of significant figures. So if you're doing something where you have a lot more precision in your data, then you want to use all the available precision you have in any other constants that you bring in. Any other questions? Let's do another one. How many liters of oxygen at STP are required to form 10.5 grams of water? And we're given a chemical equation. This is stoichiometry again, not just because it says so in the title, but we've got oxygen and water, 2 different substances. That's a clue that stoichiometry is involved. Well, we've got 10.5 grams of water, so let's write that under the balanced chemical equation here. 10.5 grams of that. Then let's look at the question, how many liters of oxygen? So question mark, liters. What other information are we given? At STP. Okay. It's just sitting there in parentheses, but that's really important. That simplifies things. Because that means we can use the molar volume of a gas at STP. So this is how many liters. That didn't work well. At STP. Uh-huh.
Since that's for liters of oxygen, I'm guessing that's oxygen gas.
Yes.
Since it's diatomic, that will be O2.
It would be O2. Mm-hmm. Right. It's liters of oxygen gas, O2 molecules. Yep. Okay, so stoichiometry is usually grams to moles to grams, but this time we're going to liters at the end. So it's going to be grams of water. I'll write this down. Grams of water to moles of water to moles of oxygen. Now instead of grams, we're going to go to liters of oxygen. So we start with 10.5 grams of H2O. Go to moles of H2O. We're going to be dividing by grams of H2O so the units work out. Then we're going to moles of O2. And down here, moles of H2O. And then we're going to liters of O2 divided by moles of O2. So we need a mole ratio for this middle term. 1 mole of oxygen, 2 moles of water. 1 mole of oxygen, 2 moles of water. We need the molar mass of water. I don't think we need to go over how to calculate that. It's 18.016 or 18.02, whatever. Liters and moles of oxygen. Because it's at STP, we don't have to use the ideal gas equation. We can use the molar volume of a gas. So it's 22.4 liters per 1 mole of oxygen. Now, if you forgot that number, as long as you remember what STP means, that the temperature is 0 degrees Celsius, 273.15 Kelvin, and the pressure is 1 atmosphere, you could use the ideal gas equation to calculate the volume from the number of moles. It's just some more steps.
Are you going to give us in the test, like instead of making us do the ideal gas law to find the molarity of O2, would you give it to us, or would you just provide information for us to solve it using ideal gas law?
Well, there will probably be a test question in which you get to use the molar volume of a gas. There will also be questions where you have to use the ideal gas law to calculate.
Oh.
Yeah, and it's not actually the molarity. I know it looks like that because it's moles per liter, but it's the volume of a mole. Yeah. So 10.5 divided by 18.016 divided by 2 times 22.4. So I'm getting 6.5275. Here's another, this is another one where we're going to have 3 significant figures. So 6.53 liters of oxygen gas. Questions?